Well, let's get started here. Thank you again for having me and allowing me to present on a project that the county has been working on for some time. It dates all the way back to 2010. But before I dive into kind of this manure processing, just to give folks a little lay of where we're at here in Wisconsin. So Dane County is located in South Central Wisconsin, located down here kind of in the red box. In addition to that, what kind of makes our county pretty unique is that we tend to be home to pretty heavy agricultural systems as far as counties go throughout the state of Wisconsin. So Dane County has over 375,000 acres of active agricultural land. In addition to that, what also makes our county pretty unique is that we're the only state capital that's located on an isthmus. So what that entails for us is that we have a plethora and quite a bit of water resources throughout the county, over 26,000 acres of surface water. And so when you mix those two together between ag and water, you oftentimes get some challenges. As I mentioned before, agriculture is part of our identity. We really kind of lean into that and what makes our county very unique. In addition to that, that agricultural impact that we tend to see within the county is pretty significant. And so we oftentimes acknowledge that as well. The county has an annual economic impact from agriculture around $3.1 billion. And so that's by no means something we want to neglect or take for granted. In addition to that, I mentioned our water resources and how that's very important to us as well. We recently conducted a study to kind of try to quantify what the economic impact is from that resource. And on an annual basis, that's over $22 million. So certainly we see the value from just those economic perspectives of both of these resources within the county. However, as I mentioned before, a lot of times when we have both of these resources, there comes some challenges. Manure contains a significant amount of nutrients, and the one in particular that oftentimes impacts our freshwater systems is phosphorus. So most of the freshwater systems you'll see tend to be negatively impacted by phosphorus. Certainly, I don't want to neglect the Gulf of hypoxia issues or some of our coastal states that may be online as well, because recognizing that a lot of times nitrogen is driving a lot of the water quality issues as well. So in addition to that, I wish I could sometimes control the weather a little bit better than what we can. As much as I would love to prevent runoff, it just is inevitable. Usually when we get especially with some of the climate change issues we're facing, we're tending to get more frequently and intense rain events. Those rain events on agricultural land cause runoff, which in turn that runoff brings phosphorus to our lakes. So some of the UW research that's out there has shown that 1 pound of phosphorus is equal to roughly 500 pounds of algal growth. And you can see kind of in the picture down here on the lower left-hand side that oftentimes this is all blue-green algae that you see growing here. So recognizing the challenges of kind of balancing both of these resources, we wanted to try to find maybe some solutions on how manure and namely phosphorus could be better managed. So sticking with the theme of manure, some of the challenges that we tend to have here in our county is the distribution of where manure is. So this map here is showing where all of the manure storage structures are within the county that we currently have inventoried. You certainly can see that it's not equally distributed. There tends to be a larger concentration of livestock agriculture, and in particular, that's usually associated with manure storage. So we tend to see larger concentrations of manure in the northern part of our county, especially in the north central, which is the headwaters of our watersheds. As you can see here, here's where our lakes are located, and the capital's right here on the isthmus. So everything up here in the north flows from north kind of to south. In addition to that, we also understand some of the challenges regarding the concentration of nutrients within manure, especially as it's related to phosphorus. So oftentimes our manure applications are really targeted and focused on trying to deliver the nitrogen needs for a lot of the crops that are being grown. And so an adverse impact is that oftentimes we're over applying the amount of phosphorus that we really need to have out there in our systems. Certainly other challenges related to manure comes in our transportation. How do we get manure to fields that maybe need it, especially when it's more concentrated in a specific area? As well as scale. So oftentimes we have a variety of livestock agricultural types, ranging from concentrated animal feeding operations or large-sized dairy operations to the small-scale farms as well. So the next map that I have here is showing a little bit of what some of the adverse impacts have been with just livestock agriculture in our county in particular over time. So this map is showing the soil test phosphorus levels that we have within the different watersheds throughout the county. And so part of the impact that we tend to have is what we like to call a legacy impact, or just kind of the continuous operations of livestock within a given area tends to result in the buildup of soil test phosphorus levels within our system. So as I kind of showed you where livestock is located within the county on the previous map, you can see that it was concentrated up here in the northern part of the watershed. And certainly you can see that that particular watershed has the highest soil test phosphorus levels compared to other watersheds throughout the county. All right, so going into a little bit on coming up with some manure management solutions. So going back in time a little bit, what really prompted what I'm about to show you here was some events that occurred in around 2005. We had a number of fish kills, unfortunately, within our county where agricultural runoff, namely manure, was responsible for impacting some of the trout streams that we had within the county. Around that same time as well, the EPA, as well as our Department of Natural Resources that we have within here in the state, was also looking at developing our state's first, what they call total maximum daily load. For those that are familiar with that term or what that means from a regulatory perspective. And so a lot of us at the county, as well as the state agencies that we have here, we're starting to collaborate both in developing this what they call total maximum daily load. The easiest way I can explain that is that it sets somewhat of a prescriptive, or I guess a target goal, in the amount of phosphorus as well as total suspended sediments that we were hoping to achieve within our surface waters that we have within not only the county, but other counties that have the Rock River TMDL in it. So in reaction to both of these kind of events that were occurring, the county pulled together state agencies as well as farmers, a lot of different farmer groups, nonprofit organizations, and really started to try to kick around some different ideas on how we might be able to combat this and both manage our manure a little bit more appropriately, but also try to improve our water quality here within the county. And so that effort stemmed what we call the Yahara. We call it Yahara Clean. It's since been rebranded because this initiative has been ongoing for some time and is now called Renew the Blue. But in essence, again, it's working with tons of different community members, both on the urban front as well as the rural front, given that the TMDLs are trying to address both what we call point source discharges, or like your industrial components of discharges directly to streams, as well as that non-point component, which we often associate with kind of more of the rural or agricultural setting. And so all these folks kind of came together. We threw around 70 different recommended solutions, ranging from erosion control for construction sites, all the way to different manure management solutions for winter spreading. And ultimately, one of the ideas that was suggested from that was a community digester. And so I'll be presenting a little bit more on kind of how we brought that idea to fruition. So the first step in trying to move that forward was we figured we probably should try to conduct a feasibility study. The concept of digesters wasn't new. We knew that Europe had been using them for some time, but we were very interested in how we might be able to pull that off within our community, given the types of agriculture we have here. And so we set kind of a goal for that study in ensuring kind of these three pillars. We wanted to ensure agricultural viability and sustainability for our farming community. We also knew it needed to be economically feasible. At that time, if you remember kind of back to 2008, there was a pretty significant recession kind of going on from housing. And so we were trying to find ways, well, even though we have this idea and concept, how can we get this to kind of cash flow? In addition to that, we also wanted to keep the water quality protection as one of the big focuses of this as well. And so we really were going beyond just what a typical digester had originally been used for those that are familiar with that, and more of trying to collect manure and use it as a methane or renewable energy source. We really wanted to bring in this water quality protection component within the system as well. And so some of the big questions that were always asked at all the meetings, and these meetings included sitting down in the milk houses with farmers, speaking at town hall events, really trying to get everyone's perspective some of the big questions were, well, what are the benefits for the farmer? Who pays and how much? I think that's just inevitable about any big, large capital projects. And then again, how do we protect the water? So building off of kind of those three pillars, here's kind of some of the goals that we really set out. So from that ag viability standpoint, we really needed to ensure that our solution did not have a significant cost, or actually we tried to hit no cost to our farmer participants. Some of the big themes we heard from the farmers was that they really wanted to see a reduction in the volume of manure. And I think that's where we can talk a little bit more about this ultrafiltration reverse osmosis as a solution for that. We also heard pretty resounding was that they wanted less phosphorus rich manure. In essence, because of this imbalance within the nutrient concentration in manure, they're tending to be more phosphorus than needed when trying to apply it to nitrogen requirements or needs. They really were hoping to get a product back that had less phosphorus in it. From that economic feasibility standpoint, we realized early on that it was probably going to have to be a public-private kind of ownership structure, just because these were significant capital expenses in order to build a facility like this. And then we also were discussing, given that digesters are able to capitalize on some of at least the energy markets at the time, whether that was electricity or whether that was natural gas, and since then some of the carbon markets that are out there. Some of those revenue streams would hopefully help offset some of the operating expenses associated with this water quality component that we have on the back end. Because there really isn't any economic drivers when it comes to water quality. We can monetize a lot of those, but in just the actual, let's call it free markets or capital markets that exist out there, there's no way to really tie into those for improving water quality. And then the last pillar that I mentioned too, as far as this water quality component, we built into all of the agreements that we have with all the participants, what we call lease requirements, which set a standard for the private ownerships of these facilities. It stipulates that they have to remove at least 60% of the phosphorus in the manure that comes into that facility. In addition to that, we knew that just because we remove the phosphorus doesn't mean there still isn't a risk for water quality. And so we also require all of our participating farms to abide by what we call a land spreading requirement or agreement. In essence, what that does is really focusing in on what kind of the phosphorus balance is on the fields that they're applying these manure products to, and trying to build a drawdown for some of those fields that have really excessively high soil test phosphorus levels, so we can start to kind of combat some of this legacy effect that we have with phosphorus building up in the soil. And so kind of this system here was unique in that a lot of our conservation practices that we implement at the county are really focused on kind of the runoff, like transport and delivery of nutrients to surface water, where this solution here was the first one that really tried to get at, well, how can we get phosphorus out of this manure nutrient, so that way maybe it could be transported out of our watersheds into areas, again, at that map that I showed at the beginning, to areas in the county that are not as heavily livestock agriculture, right? Certainly there's values for these nutrients. Maybe they could be used outside of the watershed in more of a cash grain agricultural system. All right, so that feasibility study was completed, and out of that, in working with a lot of the farmers in the area, we were able to identify two sites for potential facilities. So our first site was Wanakee, which is a picture of it down here below. That was our first site, which was built in 2010. And then our second site, which is Middleton, which is this lower star that you see here, was commissioned in 2013. So both facilities, the Wanakee and Middleton facility, have some equipment that are the same at both sites. So they both have three 1.25 million gallon digester tanks. So in essence, that's where the magic happens when the manure comes in to create and capture that methane that can be used to create energy. In addition to that, they also have a system of centrifuge systems as well as screw presses, focusing really in on that solid separation. That's where we were able to get a lot of the phosphorus reductions that we set out to try to achieve with these projects. They're located primarily within the solids, and so this equipment gets us to that water quality component. In addition, both facility are now have an RNG offtake facility. So RNG stands for renewable natural gas. So when they were originally constructed back in like 2010 and 2013, we were using the gas that was generated at the site to power gensets right on site to create electricity that we then sold back to the utilities that we have here in the county. And so that was really lucrative at the time. We entered into what is called a purchase of power agreements, which made these systems cash flow really well for the first 3 to 5 years of these projects. However, once those purchase of power agreements expired, there wasn't a large incentive to create electricity from methane. But about at that time, fortunately, the California carbon market really started to open up, and both facilities were able to pivot to capturing that methane, cleaning it through the RNG offtake facilities. And the county owns an interconnection to the interstate pipeline that goes to California. And so we were able to give them a connection point into the line so they could sell this renewable natural gas on the California market. Each facility also currently has 5 participating farms for both sites. When they were first commissioned, each site had 3 participating farms. So we have seen growth in farm participation in both sites as well. All right. What makes Middleton a little bit different, and that's the one we'll focus in on here a little bit more, is it has a 71,000 square foot solids building, which really helps on us trying to move forward other uses for the solids that are separated out of the manure. So a private company is working on composting this, and so we're able to start some of that composting process within the solids building. In addition, Middleton also has a 15 million gallon storage lagoon. So one of the things we learned from building the first site was that manure storage was highly sought after, just from an operational standpoint. On if you have to do maintenance or you need to do anything on site, it gives you some flexibility on where you can put that manure when it's coming in temporarily until you can get things back online. The facility also went through a solar microgrid upgrade. So in essence, they have solar panels on the buildings, they have solar arrays out there. That helps in their LCFS score in the carbon market. And so they're able to produce a lot of the energy demands that they have for their facility on site, which helps them get a premium on the gas that they're selling to California. In addition, this facility also has an ultrafiltration and RO system on it as well. So this was moving beyond just the solid separation that we originally had at our first site and really trying to get as much phosphorus out of the manure as we possibly could. In addition to also discharging clean water, which was one of the major goals we had with the participating farms and them wanting to see kind of that volume reduction in the manure that they're sending to the facilities. So along with that, we also have a surface water discharge for that RO water that is returned back to the stream. All right, so the next slide that I have here is to just outline a little bit of how the manure works through the system and how these different components that I just kind of listed off are connected. So we'll start up here. When we look at our Middleton facility, we do have one participating farm that's in close proximity to the facility. And so manure is actually pumped directly from their farm to the site. The remaining 4 farms are trucking their manure to the site. And so all farms manure goes into what's called this reception tank. So from there, that manure is mixed and then it enters our digesters. As I mentioned before, when the facilities were first created, a lot of the focus was on the creation of gas to run the generators to produce electricity. And so the original model had a lot of substrates also coming into the system, which helped the economics of these from an operational standpoint, and that there was tipping fees for substrates that were brought in. The current digester owners at that time found value in that because it helped create the gas that they wanted to run their generators. However, with the pivot to renewable natural gas and really trying to tap into that California market, substrates have now been removed from the system at both sites. There isn't as much of a value from that tipping fee in compared to the value you get from not adding substrates and the value of the energy that's produced from that manure. So since then, substrates are no longer added to either facility. Our participating farms also enjoyed not having to add substrates because that just added another kind of complexity of, well, what's coming back to my farm from a land application standpoint. So once it goes into the digesters, there's a whole other pathway here for how the gas comes off of those systems. But the manure itself then enters into a screw press. So this facility has 3 screw presses that help remove that solids fraction from the manure, which then those solids off the screw press go to our solids composting building. The centrate that we call it off of the screw press then enters a centrifuge for further solids removal. That goes to the solids building. And then the centrate off of the centrifuge actually comes into the front end of our ultrafiltration system. So from there, it runs through an ultrafiltration as well as a reverse osmosis system. So the products off of both of these come back to the manure tank where they get commingled and get land applied for the farmers that are participating in the facility. However, the other product that comes off of the reverse osmosis system is that clean water fraction, which is discharged to Pheasant Branch Creek, which is, I think, maybe, I want to say maybe 300 yards from the facility, so fairly close. They don't have to run too far to get to that discharge point. All right. So from an operational standpoint, I got some numbers here of the performance that the RO and UF systems had in the past. So on a daily basis, the digesters, after it comes off of the centrifuge, was sending roughly 22,500 gallons per day to the ultrafiltration system. So from there, when you go through the different paths and you separate it, this is kind of what the material looks like that comes in on the front end of the ultrafiltration system. I apologize that the picture is not very large to see, but just to kind of give you an idea as this manure gets processed, what it looks like, as well as what the volumes are coming off of the back end of the systems. So this goes into the UF system, around 17,000 gallons per day from the RO and UF system, which are these 2 components that you see in these jars, gets sent back to the digester. And so this is the material that goes back to the farms. So this is the liquid fraction that would not be discharged. Becky will go into a lot more detail about what the nutrient concentrations are within each of these different systems, how they could be possibly used on the farm. But one of the big things and goals that we had for the project was really trying to get the clean water out of manure. And so after it goes through the RO system on the back end, roughly 5,500 gallons a day is able to be discharged to the stream. So when we look at that as a percentage value, it's about 25% of the total volume that comes in on the back end. And so that's may or may not be considered a significant reduction of volume depending on where you're at your operations and what your end goals are for the clean water that comes off the back end. This system that we've showed here, they've been testing now for a while, and they figure they can roughly get about, on a maximum kind of performance standpoint, about 33% of the liquids that come out of the system they can kind of get from the UF system. Another third is usually coming off of the RO system, and then if you really push the system, you can maybe get about a third of clean water. That's in stark contrast to what the original owners of the facility told us we could get from a performance standpoint. So the company that owns this system now is the third owner, and they've done a lot of different changes and have learned a lot along the way. The original owner of the system gave us a guarantee of 50% clean water. However, we were never able to actually achieve that level of performance. And one of the big kind of take-home considerations I would caution everyone who's maybe looking at these systems is the percent TSS in the manure that's coming in on the front end, hitting that UF system is really critical. That's been kind of the linchpin that we've learned in working with these systems. You really need that TSS to be really low. Like 1.5% is maybe a workable number to work with, but a lot of the manure, even after it comes off the screw presses and the centrifuge, are still north of 2% TSS. And that really makes it a challenge for these systems to run efficiently because they're either constantly cleaning them and they just can't get the throughput of the system. In addition to that, I also would caution when we built this, we tried to make this scalable. So it's modular and that we can add more filters and membranes to the system as the system grew. At the time when we spec'd this out, we had roughly 60,000, I think, gallons per day coming into the digester facility. Since the point at which we commissioned this system and new owners took over the digester operations, we've doubled the amount of manure coming in. So I mentioned before that we added farms, and so we added a pretty significant source of manure that really wasn't able to keep up to kind of the design that we had originally commissioned out there. Two other factors to kind of keep in the back of your head too is consistent flow. So within digesters, any type of mechanical operation, you're going to have downtimes for either fixing things or maintenance. And it's really, I think, these run most efficient when you can keep that uptime and a constant flow through the system. And then the other one is that design capacity, which I touched on before, is just even though they're modular and scalable, just I would say go in the front end of kind of overbuilding for what you think your current needs are, because I think you get a little bit higher level of efficiency, both from an RO discharge standpoint, if you're looking for water reclamation, and just from a maintenance standpoint all around. They're not having to work as hard. So looking a little bit as far as the phosphorus removal goes, I've got some numbers here that I just was going to share with you all. So from both of our facilities, so I mentioned we have our original one up in Wanakee and our Middleton facility. This is showing the total pounds of phosphorus that are removed from both sites. So if you remember from before, I said that each facility is required to move at least 60% of the phosphorus. They don't always hit that target, but what that looks like from a pounds perspective of phosphorus based on the manure that's sent there. So in 2022, we were just shy of 250,000 pounds of phosphorus. 2023 was probably the best performing year. They had done some significant maintenance on the centrifuges, screw presses at both facilities, and we're getting some pretty high performance. So we actually surpassed 300,000 pounds of phosphorus. And then in 2024, we were just shy of that 300,000 pounds. So pretty significant amount of phosphorus being removed from the manure from both of these facilities. So kind of one of the last slides that I have here is just to kind of put that in perspective of, okay, so here's the pounds of phosphorus that's removed, but how does that actually match up to some of the other manure generating numbers that we have throughout the county? So this picture here is showing the green line is the outline for all of Dane County. The black line you see here is the Yahara River watershed. So that's the watershed that's within the Rock River TMDL that we're really focused in on trying to get phosphorus levels reduced in. And then the red line here depicts what's called the North Mendota watershed. And so that's the watershed that has the highest concentration of livestock agriculture. And so here's a table just showing the number of animals that we're estimating within each of those different boundaries. So Dane County is at 155,000. The Yahara watershed at 79,000, and then the North Mendota watershed at about 60,000. And then we can use those animal numbers to estimate what the total gallons of manure is within each of those boundaries, as well as the estimated total pounds of phosphorus in that manure for those different geographic areas as well. So using the 2024 numbers for the phosphorus that were removed, we were able to look at just from a manure processing standpoint. So in 2024, both facilities processed over 128 million gallons of manure. So that's a lot of manure coming through both of those doors. And that accounts for about 12% of all the manure in the county, as well as 24% for the Yahara watershed and 30% for that North Mendota watershed. In addition, we can also look at it from a pounds of phosphorus perspective, because as I mentioned before, that's another thing we're concerned about. And so if you look at the numbers here, we were just shy of 300,000 pounds of phosphorus in 2024. So that accounts for about 7% of the pounds of phosphorus for manure for the county, 13% for the Yahara watershed, and 15% of the phosphorus for manure in the North Mendota watershed. So a lot of times we get questions asked, well, how much is that in relation to all the manure? And so here's just kind of a breakdown for how those numbers pencil out. All right, so I'd be remiss if I didn't talk a little bit about the permitting and the regulations associated with these discharges and running these facilities. So here's just kind of a short list, not that short, of all of the federal and state regulations that we have to deal with in the state of Wisconsin. So I'm not counting any of the local regulations as far as construction, what you would need to build a facility. This is just looking at the regulations associated with managing the manure and the clean water discharge. So The Federal Clean Water Act is a big one. So because we were one of the first watersheds to have a total maximum daily load from the EPA, Pheasant Branch Creek, the stream that we discharge the clean water to, actually is a 303D listed impaired water body. So there's a lot more regulations as it relates to the quality of the effluent that you need to attain in order to discharge that water. In addition, we have a lot of Wisconsin state statutes around what we call Wisconsin Pollution Discharge Elimination System, or WPDS. So this is kind of that point source discharge that regulates a little bit of our larger farms from that CAFO perspective, as well as the facility itself that's discharging the clean water. So we have NR 102, NR 212, effluent standards, phosphorus limits. I also have in here NR 151. This is the runoff standards for a lot of our smaller farms that don't meet that definition of a concentrated animal feeding operation. One of the harder ones that we have, and what makes a little bit more of a challenge here, especially in Wisconsin, is we're one of the only states that has effluent standards and limitations on phosphorus. And so there's actually site-specific criterion that we have to meet in order to discharge the water to Pheasant Branch Stream. In addition, we've also got some local rules and regulations under our Chapter 49 Agricultural Performance Standards and Manure Management. This gets into a little bit more of the storage of those different manure products that we have on the back end, and also the storage on the farms. All right, so the next steps, where we're at right now on kind of this journey and looking at manure management as a solution is we currently have a feasibility study that we decided to redo. So our first one was done back in 2010. We decided to try to update that to look at a lot of different components. We've shifted kind of those three pillars that I had at the beginning of the slides to looking at protecting and improving water quality, which was kind of still the same, but we were shifting the one on kind of the farm sustainability and the economics to really look at creating a valued agricultural product on the back end. We still have this challenge with the solids that we remove through the screw presses and centrifuges. We'd love to find markets for that that are a little bit more sustainable and stable, so we can kind of stay plugged into them and trying to find different uses for those materials on the back end. And then we're shifting also because we have a county climate action plan. Certainly CO2 and carbon is on our minds here in the county, and we're trying to find ways to investing in more sustainability and carbon related projects as well. So hopefully the deliverables we'll get out of this feasibility study, which I should have available and online, hopefully within the next few weeks, is looking at recommendations on manure processing locations and components. In addition, we're looking at that byproduct market analysis, a little bit more on the business structure, on just how that would all be function and work collaboratively with everybody and all the different participants, as well as what we call an economic cost analysis. So really what's some of the capital costs, the operational costs associated with these different technologies and how we can get them to all work together to try to move something forward. All right, and with that, that's all I have for now. I do have on this slide here our website where we have our community manure management, more information for folks that are interested. Feel free to check that out. Once I get the feasibility report updated, I'll have it posted here. Otherwise, here's my contact information as well. And Becky, I will turn it over to you.